Okay, the next form of integration that we're going to talk about is integration by substitution. Integration by substitution is really undoing the chain rule. That's what we're going to be looking at here. And so if you're given something that looks like this, and this is a great pattern for us to keep in mind, is that if we've got this function, but then part of that function over here is the derivative, then we can do a U-substitution. And that's usually about the only way we can do the integration. And notice below that they're giving us 3 specific steps that we'll be going through. And we'll walk through those steps and the problems, and they won't seem near as intimidating. And the pattern that you really need to look for here is going to be an outside function, an inside function, and then that's the derivative of the inside function. When we do that, we should get something that looked like a function before we did our chain rule. Right, if we look for our pattern recognition here that we just talked about in our previous slide, notice this portion sitting out here is the derivative of your given portion. And so that's going to be a big indicator that we need to do a U-substitution. And what we'll do is let U be equal to this portion inside here, that inside function. And then we're going to take the derivative of U with respect to X, and that's going to give us a 2X. Now we'll need to solve for dx because that's part of what we'll be solving for. When we're going back and doing our U substitution, I want the integral of U du. So I'm going to multiply dx over, and then I'm going to divide by 2x. And notice when I do that, I'm going to have du over 2x is equal to dx. So now I have everything I need to come back and do our substitution. We found a u value and we found a du value. So when we rewrite our integral, we're going to take all of this x squared plus 1, that's going to be replaced with u, and it's going to be squared. And then notice that we still have a 2x here. We've not replaced. And then dx, we said we can replace dx with du over 2x. And hopefully we see that we can do some canceling here with this 2x and that 2x, and that should happen every time. You should have something there to cancel. So you're left with the integral of u squared du. And again, we're back to our traditional integration rules. We're going to add 1 to the exponent. That tells us what to divide by. We don't have endpoints, so we're going to put plus c. And now we have to keep in mind we did not start our problem with u. So we're going to have to change it all back to what it was originally. So my final answer is going to be x squared plus 1 all cubed over 3, and then plus c. And we have our U substitution and our final answer. All right, let's move on and do another one. And the more we do, the better off we're going to be. All right, so for number 4, or I'm sorry, part B, not number 4. Notice that we don't know anything about the integral of all of this. Now we do know something about the integral of cosine. If we just had just plain old cosine of u du, then we know when we integrate cosine, then that's going to give us sine. So that's the form we're really going to, is if we could get all of that just to be a plain cosine of u. So our best way to do that would be do a u substitution with the angle. So I'm going to let u equal 4x. So then du dx is going to be 4. And again, I'm going to multiply that dx over, and then I'm going to divide by 4. So du over 4 equals dx. And now we have our u value and we have a dx value. So let's go plug in. So I have the integral of 4 cosine, but I know 4x is where I'm going to place the u, and I know dx is equal to du over 4. And so again, we have some canceling, which is good. That's what should be happening. And so I have the integral of cosine of u du, which is what we wanted. And so we know that's going to be sine u plus c. But again, we did not start with u, so we're going to have to go back up and replace u with 4x. And then we have plus c. And again, we are looking for patterns. And so I know this problem looks horrible, but look for your inside function. And in your mind, take the derivative of that inside function. And notice it does generate this outside function. So that's your chain rule going on. And to undo that chain rule, this is where we're doing our U-substitution. So we are going to let our U value, that's going to be equal to the inside function. And usually by now people are asking, do I do that every time? Yeah, just about. Of course, you do have your weird problems, but just about every time you would. Notice when we do the derivative of u with respect to x, we get 8x. And again, we do need to solve for dx. So I'm going to multiply that dx over. So I have du equals 8x dx. Then I'm going to divide by 8x. And so notice that dx is equal to du over 8x. So here, when we come over, we have our 8x. We have the square root of 4x squared plus 1, but we said that was going to be our u value. And dx, we need to replace it with du over 8x. And again, notice those 8x's should cancel. And so I'm really talking about the integral, and we need to change that u to the 1/2. And then we're back to adding 1. And so let's see, that's going to give me u to the 3/2. So the coefficient is going to be that reciprocal. And then plus c, because again, we don't have endpoints, but then we do have to change that u value back. So we have 2/3 times 4x squared plus 1, all raised to the 3/2 plus c. Right, continuing on, and we do need to look for, again, those patterns. And notice inside here, if we do the derivative of this inside, we get 2x. Well, out here we have an x. As long as we get a constant value there, then we're welcome to go ahead and do the U-substitution. And all we'll need to do to adjust for that would be really to move a value. And since that's a constant value, it's okay to move it. So let me show you what that means. We're going to say u equals x squared plus 2 du. It's going to be a du dx is going to be equal to 2x. And now again, we're going to solve for dx. So I'm going to move dx over. So I have du equals 2x dx. Divide by 2x. And notice that we have dx is equal to du over 2x. So let's go plug in what we know from our u sub. We still have our x. We're going to let x squared plus 2, that's going to be u, and it's still raised to the third. Now dx, notice we found that to be du over 2x. So notice what we're going to be able to do is cancel out the x's. We have 2 left, and really that's the same thing as a 1/2 since it's in the bottom. Since that's a constant value, we can move out that constant. Now, if it was a variable that was left, we would have to go back and try something else. But since it was just a constant value, we can continue on by just moving out that 1/2. So if we continue on with our integration, we're going to have u to the 4th over 4 plus c. And then that's really going to condense to be u to the 4th over 8 plus c. But then we're going to go back and sub in our u value, which was x squared plus 2 all over 4, I'm sorry, raised to the 4th all over 8, and then plus c. Okay, again, I would look for a pattern here. Let's see, if we did the derivative of that, that's going to give us 8x. And so notice that x is kind of what we already have. So I think it'll be all right to do a u sub here. So we're going to let u be equal to 4x squared plus 3. And so the derivative of u with respect to x is going to give us 8x. And then we're going to solve for dx. So again, multiply dx over. So du equals 8x dx. And then we're going to divide by 8x. And so notice that dx is du over 8x. So let's come back over here and plug in. We didn't substitute anything for that x in the numerator. 4x squared plus 3, that's going to be our u value raised to the 6th. And then dx is going to be du divided by 8x. So we do need to check to see if anything's going to cancel. And good thing these x's do cancel. So I know I'm probably doing this correctly. 8's in the denominator and it's a constant. So I'm going to move that out. That will be a 1/8 since 8 is in the denominator. And then the integral, and we do need to flip over that u to the 6th, so it's going to be u to the negative 6th du. And now we can do our integration. So that's going to be u to the negative 5 over negative 5 plus c. And so here, that's going to end up giving us u to the negative 5 over negative 40 plus c. And then we need to go back and fill in our values. So when we do that, we're going to end up with 1 over negative 40 times 4x squared, because we're moving all of those negative exponents back down to the denominator, plus 3, and that's all raised to the 5th, and then plus c out to the side. Okay, continuing on. Again, I think by now y'all are catching on. We're probably going to let that inside stuff be u. So we're going to go ahead and do that. So we have 7 minus 2x cubed. Do the derivative of u with respect to x. We're going to have negative 6x squared. Solve for dx, so that means I'm going to multiply this over and then divide that other portion. So du over negative 6x squared equals dx. And so we're ready to come back over here and do our substitution. And notice that the 7 minus 2x cubed, that's going to be our u value. And it's still raised to the 4th. We have our x squared value. And then dx is going to be du over negative 6x squared. And again, you know you've done this correctly because we're seeing those x squared should be canceling. And so we have the integral. Now, here's where we need to rewrite this. And do remember, it's exponent over root. So it is u raised to the 4 over 3 du. Now, that negative 6 gets moved out, and it's in the denominator, so it's negative 1 over 6. So now we're back to our regular integration process. We're going to add 1 to our exponent. So that's going to give us u to the 7/3. And so 3/7 on the outside plus c. And now we can go back to what we had originally and try to clean up some of this. You would see all of this reduced down. And so that's going to give you negative 1 over 14 times, and our u value was 7 minus 2x cubed. And that's going to be raised to the 7/3 and plus c. All right, in our next problem, we are going to bring in some trig, so don't freak out. But again, underneath here, That's probably going to be the inside function. And so I'm going to let u equal sine x plus 2. And so the derivative of u with respect to x is going to give us cosine of x. And solving for dx, we would multiply dx over, divide cosine. So I'm going to have du over cosine x equals dx. And so coming back over here, we're going to have cosine x times the square root of u, and then dx is du over cosine x. And again, those cosine x's cancel, awesome stuff. So we're back to integrating u to the 1/2 du. And hopefully by now that's going to be u to the 3/2 and then 2/3 in front. We are seeing that pattern, hopefully. And then finally, we just go back and replace our u. So we have 2/3 times sine x plus 2 and then plus c. All right, and then h. And a lot of times we have a pretty good understanding of what's going on, and then we see e and our brain just like gets fried for whatever reason. Do remember that if we integrate, let's just say e to the x dx, we get back e to the x dx. And also let's remember if we were taking the derivative of e to the stuff, remember if we were doing that, then that gave us stuff prime times e to the stuff. And so notice here's where that derivative sits, and here's where the original is. So go back up here, and so usually that I get asked, well, does that mean the x or the e raised to the stuff, is that always going to be your u sub? And you're close. It's going to be most of the time the exponent. It's this portion right here. And ask yourself, if I do the derivative of 4t cubed, does that generate for me 12t squared? And if it does, then you already have the answer there in front of you. Let's go through our U-Substitution to see why, but then after this, you are more than welcome to use this little shortcut here. So we're going to let u be equal to 4t cubed. And again, we're going to do the derivatives with respect to t. Du dt equals 12t squared. So there it is. Okay. Just like all the others, we're seeing those parts. We still solve for du, so I'm going to swap those places. So du over 12t squared equals dt. And now we're ready to go do our sub. So we have 12t squared times e to the u, because that exponent became u, and then dt is du over 12t squared. And notice in our canceling, which is, we should have something to cancel here, notice both the 12s and the t squareds are accounted for. So notice that all of this simplifies down to be the integral of e to the u du, which is just e to the u, and then plus c because we don't have endpoints, and then go back to what u was equal to, and that's going to be e to the 4t cubed plus c. So there's our answer, which will always be this main function right here, as long as the derivative of the exponent is that coefficient there. That always works. So if you want to learn it that way, you're welcome to, but seeing u does not change your process. And the same thing's true for the next set of problems. Again, we need to go over and remember, well, what was the derivative of the natural log of x? It was 1 over x. So let's put that over to the side to remind ourselves that if we did the derivative of, and we called it natural log of stuff, we said that was stuff prime over stuff. We said that every time. So let's look at this and see what's going on with it. Now, this x in the denominator always freaks out people. They're like, oh, I don't know, I don't know. It'll be okay. You're more than welcome to separate this out if you want to, or leave it. When I say separate it, sometimes it's easier for us to see that that's 1 over x times the natural log of x dx. Sometimes it helps to rewrite it, and let me show you why. When we go through our u sub, so in other words, I'm going to let u be, and our main function is right here, is that natural log of x. And when I do the derivative with respect to x, I'm going to have 1 over x. Again, derivative natural log of x is 1 over x, because the derivative of x is 1. There's your stuff prime over stuff. And again, we're going to change places with these two. So if we do that, I'm going to multiply that dx over. So I have du equals 1 over x dx. And to solve for dx, I would multiply both sides by x. So I have x du equals dx. So let's go back up and substitute in. I have my 1 over x. I have natural log of x, but that was u, times dx, which we said was x du. And now notice what cancels. These two things cancel. So all I'm left with is the integral of u du. And then if I integrate that, remember that's going to be u squared over 2 plus c. And so u was natural log of x, and I would put parentheses because you need to make sure the entire function is squared, not just the x there. So do put parentheses around it. And then plus c. So don't freak out whenever you see those types of problems. All right, so here's another one. Great example of what to be expecting. And again, notice here and here, it kind of looks like they're both like major functions. So pick the one with the exponent. Let that be your U-substitution. So that's going to give me cosine x. So then du dx, the derivative of cosine is negative sine x. And again, we're going to solve for dx, so I'll multiply that dx over and divide by sine. So du over negative sine x equals dx. And we're ready to come back over here and do our u sub. So cosine to the fourth is really going to translate to be u to the fourth. And then we're going to have sine x. Dx is going to be changed to du over negative sine x. And notice when we cancel, we have a negative left, a negative 1. So just move that negative out. And so we're integrating negative u to the fourth du. And now we just bring that negative along. So that's going to be u to the fifth over 5 plus c. And then we go back and replace our u. So we're going to have negative cosine x all to the fifth over 5 plus c. Here's a good example of them trying to fool us. Notice this portion right here. And since that's all separated, multiplied out, then you've got this, and it makes it hard to decide. So this means we need some rewriting because nothing's really sticking out as, hey, this is what I need to let u be. And notice you've got two separate e's, but those are like bases. So really, we can bring over our 3x squared plus 1, and then that e can be rewritten by adding those exponents. So that's x cubed plus x, because you're multiplying with like bases, so you can add those exponents. So now we do have an e raised to stuff. If I do the derivative of that exponent in my mind, it's going to generate something pretty darn close to that. So let's let our u be equal to x cubed plus x. So du dx is going to be equal to 3x squared plus 1. And notice it does work out. And we're going to move our dx over and divide by that entire other term. So we're going to have du over 3x squared plus 1. That's going to be equal to dx. Now we're ready to go back and do our substitution. We have 3x squared plus 1. All of that e business is just going to be e to the u. And then dx is du over 3x squared plus 1. And we have a winner, winner, chicken dinner because those are going to cancel. And so I'm just integrating e to the u du, which we know is e to the u plus c. And then go back and replace your u value, which is x cubed plus x, and then plus c. So could you, if you get to where you're recognizing the pattern, and this does end up nice and neatly ending up being what your coefficient is, your answer is always sitting right there every time. And you could really stop working out this once you do your du dx and you notice that is everything that you have in the numerator, or not numerator, but everything you have in the original problem, then just stop. You've got the final answer there. All right, so now let's go on and look at our next problem. And again, this is one that it might be easier to see if we pull it apart. And what I mean by that is, now don't try to divide it up because we have 2 terms in the bottom, and that's just, we can't do that. Little animals die. So we have e to the 3t times 1 over 3 plus e to the 3t. And then, of course, we have our dt. So, goodness, this looks like it's just an absolutely terrible problem here. And so I would let the more complicated portion, this denominator, let's let that be our U-substitution. So I'm going to say U equals 3 plus e raised to the 3t. And so if I do my derivative of u with respect to t, that's going to give me, well, we've got to do the derivative of e to the 3t, which is the derivative of the exponent times the original term. So notice that does work out nice. Again, we are going to solve for dt, and hopefully you're seeing that pattern now with solving. So we see that du over 3e raised to the 3t is going to be equal to dx. And so when we come back up and we do our u sub, we have the integral, we have e to the 3t from the original times 1 over 3 plus e to the 3t. That's what we said we wanted u to be. And dx, or dt, I swapped variables there. Sorry, guys. So dt is going to be du over 3e to the 3t. All right, so now we're to the point where we should have something to cancel, hopefully. Notice the e to the 3t's should cancel. We have a 3 left in the bottom, so that's going to move out and be a 1/3. So I have 1/3 integral 1 over u du. And anytime we integrate 1 over u or 1 over t or 1 over x, that is every time going to be natural log. So we have 1/3 natural log absolute value of u plus c. But then we do need to go back and replace that u. So we have 1/3 natural log absolute value of 3 plus e to the 3t, and then plus c. All right, and so with our u sub, we're going to start seeing some really strange problems. Example here. And so let's divide this up into 2 separate integral problems because a u substitution here is not going to generate anything for us. So let's divide it up and say, well, the first integral I want to be is 3 to the x dx. And then the second one, I'm going to have 1 over x dx. And again, notice right here, as soon as we do that, hopefully we recognize from the previous problem, well, that's just natural log of absolute value of x plus c. Now this right here, this will always be a formula, and it's a pretty straightforward formula. The numerator of it will always be whatever's sitting here. Oh, that's 3 to the x, not 3 times x. Lord help us. 3 to the x over, the bottom is always natural log, and it's natural log of what? Well, it's going to be just that number sitting there, so it's natural log of 3. There's your answer. That is it. So a little quick, let's just make up what that formula is. Let's say we're integrating some number raised to x dx. That will always be a to the x over the natural log absolute value of a plus c. That never changes no matter what. All right, so let's move on to our final problem of indefinite. Now we do have some for definite. And again, going through here, oh my goodness, this looks absolutely horrible. So I'm going to make the biggest, ugliest crap mess of this, which in my opinion is that one. I'm going to let that be u. So I'm going to say, well, u equals sine x squared plus 5. And so when I do my derivative with respect to x, well, sine of x squared. So this is where we had to do the derivative of our angle, which is going to give us 2x, and then the derivative of sine of x, which is cosine of x. And then plus 5, well, the derivative of 5 is 0, so yay. So again, we still need to move our dx over and divide by our 2x cosine x. So we have du over 2x cosine x equals dx. So let's go back and do our u sub. We have the integral of x cosine x squared times sine x squared is really, let's see, not sine. Oh my, we let all that be u, didn't we? I need to pay attention. And then times dx, which we said was du over 2x cosine x. All right. So let's see. Are we going to get anything at all to cancel? Oh, I left off my x squared, guys. Oh no. Sorry. All right. So here we go. So yes, and notice I knew immediately. I'm like, oh, something was wrong because I had different angles, and that made me find my mistake. All right, and then that 2 is going to be moved out to 1/2 integral of u du. So notice all of that ended up generating something pretty easy to integrate. So that's going to be u squared over 2 plus c. And now we can put all this together. We're going to have 1/4 times, and u was sine x squared plus 5. And it's all raised to any power. Yeah, it's all squared. And then plus c. Now working out the problem, and the only difference with these is you're going to have these boundaries. You've got these endpoints. So it's really not going to change our process that much at all. We're still going to start the same exact way that we've been doing. So we're going to go right back to trying to pick out a u and generate a du. Well, for this one, anytime you have your trig stuff, think about, well, which one of these is the derivative of the other? And so we know that if we do the derivative of tangent, we get secant squared. So that's a good indicator that u needs to be tangent x. And so du dx will generate secant squared x. And of course, solving, we would have du over secant squared x equals dx. And then we come back over here and we're integrating from, well, normally from 0 to pi over 4, but we have a problem because if I do fill in my u values, this is going to be tangent x here. Nope, we let u be tangent x, sorry. So we're going to have u times, and let's see, we have secant squared x times dx, which is du over secant squared x. And when we cancel, notice we're just integrating u du. Now, we cannot attach these endpoints here and here. We can't attach those boundaries down here because those boundaries were for x. They're not for u. So to adjust those, and a lot of times the problems that you see on the AP exam won't even have them worked out. It'll just ask you which one's the right U-substitution. And one of the answers they're going to give you will be this U-sub with the original endpoints, and then they'll give you a different set. The different set of endpoints is going to be what we need. So you think about your U-sub now as being kind of a unit here that you can change things. So if I want to know what u is in terms of pi over 4, so you're going to evaluate this. So u is going to be equal, or the upper endpoint for u is going to be, well, what is tangent of pi over 4, which is going to be 1. So that tells me my new upper bound is 1. And so what about my other lower bound? Again, to translate that, we're going to have tangent of 0, and tangent of 0 most days is going to be 0. So there's your bottom endpoint. And you can go ahead and evaluate the problem using just this. So let's go ahead and evaluate. We know that's going to be 1/2 u to the second, and we're going to evaluate this from 0 to 1, which makes this a lot more doable. So we're going to have 1/2 times 1 squared minus 0 squared, and so we see that our answer is 1/2, which would be the same exact answer we would get if we went back up and resubbed in tangent and worked it out. So this is just a good little way of going through and actually making the problem a whole lot easier for ourselves. And again, we're only doing this because we're given those definite endpoints. So again, we're going to have to pick a u-sub, and I would pick the trig function that has that exponent. So I'm going to say u equals cosine 2 theta. So du dx is going to be, do the derivative of the angle first, and then derivative of cosine is negative sine of that same angle. Now let's solve for dx. So I'm going to have du over negative 2 sine 2 theta. That's all going to be equal to dx. And now let's go back and plug in. But again, our endpoints, this is in terms of theta, so we're going to wait to attach those. I do have sine 2 theta over what, and this is going to be a u cubed, and then dx is going to be du over negative 2 sine 2 theta. And so again, we see things are going to cancel here, and that's good. Those are going to cancel. This negative 2, it's in the bottom, it comes out and becomes negative 1/2. The integral, and now I'm going to have to flip this over, so that's u to the negative 3 du. And now let's go adjust our endpoints. So we're going to plug in pi over 6. So I'm going to come down here and say, well, our upper endpoint, we're going to say cosine of 2 times pi over 6. And so we do need to simplify that fraction because it's going to help us. So that's really going to be cosine of pi over 3, which is 1/2. So I now know this upper endpoint is 1/2. Our lower endpoint, we are going to plug in 0. So we're going to have here cosine of 2 times 0, which is still 0. Cosine of 0 is 1. So we have that. All right, now one thing I'm noticing here, our endpoints are inverted. Notice we're going from 1 to 1/2, so that's backwards. We're going to have to flip those, which is going to change that sign. So we're going to have 1/2 times from 1/2 to 1, and then we have our u to the -3 du. All right, so this problem is pretty lengthy here. Let's keep going. We've got 1/2 times, if we add 1, that's going to be u to the -2 over -2. And I want to evaluate that from 1/2 to 1. I would move this -2, definitely move that out. So I have -1/4 times, well, 1 to the -2 is still 1, minus 1/2 to the -2. Well, 1/2 squared is 1/4, and then the negative, we're going to flip that over. So that's going to be 4. And so it looks like we're going to end up with -1/4 times -3, so we should have 3/4. All right, last two problems, hallelujah. So again, quick check there, take the derivative, that does generate this outside. So we're going to have u equals 1 plus x cubed. Du dx is going to be 3x squared. And again, solving, we're going to have du over 3x squared equals dx. So go back up here, we have 3x squared, and then that's all going to be u to the 1/2, dx is du over 3x squared. And so notice those are going to cancel. And so we're ready to integrate this, but we need to adjust our endpoints. So go back and remember that right here's what we let u be. So our upper endpoint, that's going to be 1 plus 2 cubed. So I know that upper endpoint is 9. And then our lower endpoint looks like it's just going to be a 1. So now we're ready to go ahead and solve this. So we're going to have u to the 3/2, so that's going to be 2/3 out front, evaluated from 1 to 9. And so here we're going to have 2/3 times, well, 9 to the 3/2 minus 1 to the 3/2. And so we're going to have 2/3 times 9 to the 3/2. That's the square root of 9, which is 3. 3 cubed is 27 minus 1. And so let's see, that's going to give us 26. So we have 2/3 times 26, so 52 over 3. Wow. All right, last problem. And again, U-sub. And I'm looking at that denominator thinking that's probably the most crap that we have in the problem. So I'm going to let u equal, I'm sorry, not crap, awesome mathematics. U equals 1 plus 5x squared. Du dx is going to be 10x. And then swapping around stuff, solving for dx, we're going to have du over 10x equals dx. And again, integrating, we have our x that's there, the denominator is what we did our u sub with, and then dx is du over 10x. I put an equal sign there, sorry guys. And so we're going to cancel those x's. And so we need to move out our 10, 1/10 integral of 1 over u du, which again, 1 over stuff. So that's telling me that's natural log. So I know it's natural log of u. Now we're going to evaluate that. And so let's go back up and see what are we evaluating, from what to what. So we're going to plug in a 1. So that's going to give me 6. And if I plug in 0, I get 1. So here I have 1/10, natural log, absolute value. And so let's go ahead and just do this inside part. So it's 6 minus natural log, absolute value of 1. Natural log of 1 is 0, so this is going to end up being 1/10 natural log of 6.